So let's look at the Peano axioms. The first axiom states that the number 1 is a natural number. The second axiom states that if the number n is a natural number, then its successor, n plus 1, is also a natural number. The third axiom states that 1 is not the successor of any natural number n. The fourth axiom states that if m and n are two natural numbers that have the same successor, then m and n are the same natural number. And the fifth axiom states that if S is a subset of the natural numbers such that 1 is an element in the set S and n plus 1 is an element in the set S whenever the number n is in the set S, then the set S is equal to the entire set of natural numbers. So notice that axioms 1 through 3 tell us how to construct the set of natural numbers. Now, by axiom 3, 1 is not equal to n plus 1 for any natural number n, and so n is not equal to 0 for any natural number n. In other words, 0 is not a natural number. And so axioms 1 and 3 tell us that the set of natural numbers has a least element which is 1, that is, 1 is less than or equal to n for every natural number n. Now, since 1 is a natural number, which is axiom 1, by the second axiom, we have that 1 plus 1, which is 2, is a natural number. And again, by statement or axiom 2, we have that 2 plus 1, which is 3, is a natural number. And we can continue this process ad infinitum so that the set of natural numbers is the set containing 1, its successor 2, its successor 3, and so on. Now, axiom number 4 tells us when two natural numbers are equal, if m and n are two natural numbers, and these two natural numbers have the same successor, then m plus 1 is the same as n plus 1, and so m and n are the same natural number. And axiom number 5 is the basis for the principle of mathematical induction. Which we will prove shortly. So first, as a theorem, we will prove the well-ordering property of the natural numbers. If the set S is a non-empty subset of the natural numbers, then there exists an element m in the set S such that m is less than or equal to S for every element S in the set S. So proof. Suppose that the set S is a non-empty subset of the natural numbers. Then there exists at least one element S in the set S. Now, if the set S is the singleton containing this single element S, then this element is the least element of the set, since it is true for every natural number S that it is less than or equal to itself. And if the set S is not a singleton containing the value S, then the set S has more than one element. Now, if the number 1 is an element in the set S, then 1 is less than or equal to the element S for every element S in the set S, since 1 is the least element of the set of natural numbers, and the set S is a subset of the natural numbers. Otherwise, if each element S prime in the set of consecutive natural numbers from 1 to m minus 1 is not in the set S, but the successor of m minus 1, which is m, is in the set S, then m is less than or equal to the element S for every element S in the set S. So in either case, there exists an element m in the set S such that m is less than or equal to S for every element S in the set S. So as a corollary, we will prove the principle of mathematical induction. If P of n is a statement that is either true or false for every natural number n, then the statement P of n is true for every natural number n, provided that P of 1 is true and P of k plus 1 is true whenever the statement P of k is true. So proof. Suppose that conditions 1 and 2 hold, and assume that there exists a natural number n such that the statement P of n is false then the set S of all natural numbers such that the statement P of n is false is a non-empty subset of the natural numbers. So by the well-ordering property, of the natural numbers, there exists an element m in the set S such that m is less than or equal to S for every element S in the set S. That is, the set S has a least element. Now, since the statement P of 1 is true, 1 is not in the set S, and so m minus 1 is greater than or equal to 1, and m minus 1 is not in the set S since its successor, m, is the least element of the set S. That is, the statement P of m minus 1 is true, and so by condition 2, since P of m minus 1 is true, we have P of m is true, and hence m is not in the set S. This contradicts the fact that m is the least element in the set S, and therefore by contradiction the statement P of n is true for every natural number n, provided that the statement P of 1 is true, and the statement P of k plus 1 is true whenever the statement P of k is true. So let's use the principle of mathematical induction to prove that the sum of consecutive natural numbers from 1 to n is equal to n times n plus 1, all of which is divided by 2, and this is true for every natural number n. So proof, let P sub n, or P of n rather, be the statement that the sum of consecutive natural numbers from 1 to n is equal to n times n plus 1, all of which is divided by 2. We can expand this sum so that we have 1 plus 2 and so on plus n is equal to n times n plus 1 divided by 2. So P of 1 is the statement that 1 is equal to 1 times the quantity 1 plus 1 divided by 2, which is 1 times 2 divided by 2, which is 1. And hence the statement P of 1 is true. Now assume that the statement P of k is true. That is, assume that the sum 1 plus 2 and so on plus k is equal to k times k plus 1 divided by 2. Then 1 plus 2 and so on plus k plus 1 is equal to k times k plus 1 divided by 2 plus k plus 1. So if we factor out k plus 1, we have k divided by 2 plus 1, which is k plus 1 times the quantity, k plus 2 divided by 2, and so this is k plus 1 times k plus 2, all of which is divided by 2. That is, p of k plus 1 is true whenever the statement p of k is true, and therefore, by the principle of mathematical induction, the sum of consecutive natural numbers from 1 to n is equal to n times n plus 1, all of which is divided by 2 for every natural number n. So as an exercise, prove that the sum of squares of consecutive natural numbers from 1 to n is equal to n times n plus 1 times 2n plus 1, all of which is divided by 6, and show that this is true for every natural number n. Okay, so we will end here for the day. Next time we will look at ordered sets. So I hope you have enjoyed the first lecture. Thanks for watching.